Hello Physics 35, so we're going to finish off topic 8, and the entire course is all of its material today. So it won't be quite as long as last week, but we will have more math, which hopefully you will enjoy. Before we get into the new stuff, I just want to point out something in the formula sheet. So if we remember looking at our wind generated energy power, we could find the power or the energy produced per second, right? And whenever we're looking at energy per second, we know we're working with power in watts. So we discovered you could find that by taking the cross-sectional area of the propeller or the turbine and multiplying it by the rho, which is always density in physics. The density, I shouldn't say always, they like to change up variables for no apparent reason, but here rho, Greek symbol rho, is density of the air. A is the area of our propeller or turbine, and V is the speed of the wind. And you're going to cube that, and you don't have to memorize this one because it's given on our formula sheet under topic 8.1 energy sources. So we wrapped up topic 8.1 last week. We should all know energy over time is power, and we have this formula here. So they aren't giving us a formula for our wave energy or wave power. That one you'll have to be able to derive from these square waves. So that would be something you might want to study a little bit more, review a bit before you try that Smarter Marks exam. All right, so we're moving on today to, well, down the road, greenhouse gases, global warming, but we need to learn some physics before we get into that. So Stephen Hawking will take us on a little tour through that, and eventually we'll know all of these formulas today. We already kind of know intensity is power per area. I think that came up before, but we're going to look at power of black bodies. We're going to look at how wavelength and temperature are related by the Stefan-Boltzmann constant, and albedo, which you may or may not already be familiar with. So before we get into that, we need to look at radiation a bit because it's a physics 30 concept. You'll learn more about it. We're just going to need to preview that a bit. So what is fire? So the light that we actually see from flames, especially the pale blue, like we always imagine blue flames being hotter. That's because the molecules that are in the air are being excited and heated up, and as they cool down or de-energize is one way to look at it, the electrons are going to undergo atomic transitions. So as the electron goes from high energy to low energy, it's going to emit or release light. All right, so whenever something goes from high energy to low energy, it's going to emit radiation in the form of, in this case, visible light, pale blue. So even the smoke and the soot is going to be glowing because of these atomic transitions, these electrons going from high energy to low energy. But there isn't as big of an energy change or a jump that these electrons are going. So we're going to get a lower energy form of radiation, which is red. So blue and purple are the highest energy visible light radiation, whereas red is the lowest. So something that is either cooler or something that has less of an energy atomic transition will be more on this red or orange or yellow side. But let's look at why they're actually glowing. And that's what we're looking at for the first big chunk of today, black body radiation. Neat, hey? So let's look at this black body radiation a little bit more. There's a brief introduction. It's why things glow. They glow red hot or white hot even. So black body radiation is any object. So this is, again, kind of an ideal situation, an ideal model. Just like we have ideal springs, we have black bodies. It's any object that is a perfect emitter and a perfect absorber of radiation. So if you take a look at the diagram here, we have a black body that's going to perfectly absorb all of the incoming or incident radiation and then also emit all of that radiation right back perfectly. So they don't actually have to appear black. That's just what they're called. Don't think black bodies are black. That'll be the first big mistake. So a good way to remember that is to think that the sun and the earth's surfaces both behave approximately as black bodies, right? They're not perfect as a black body really should be, but they're close enough that we can approximate it. All right, now we have this black body radiation curve graph, and here it's a little bit out of order. You might see this on the internet sometimes too, but I would switch the colors here if I were you, because this isn't really what we're seeing. This should be blue, and this should be orange or yellow, and this should be red, because blue has the highest energy density, right? And this would actually be the hottest emission, right? The hottest black body would be emitting the highest energy light, which is blue. So I don't like the colors that they chose. I like this one better. This is showing the actual visible wavelengths of light that would be observed here. So you do need to learn this, and by learn I mean memorize. You don't necessarily need to memorize all of the steps, but you do have to recognize the shape and what it represents. So on the bottom we have the wavelength of the both absorbed and emitted light, right? Because it will absorb this radiation of all of those wavelengths. And that peak is what type of wavelength it is absorbing the most of, and therefore emitting the most of, giving it that color. So we'll go to that simulation later. Here is Wien's law. Wine. I don't want that. No. Here's Wien's law. This is also given on the formula sheet. It looks a little bit different. They have the maximum wavelength is equal to this constant divided by temperature. So the temperature of a black body is inversely proportional to the maximum or the peak wavelength of its absorbed and emitted radiation. So we'll only see visible light in kind of this band, in this visible light wavelength range. And pay attention to units. These are nanometers, right? We got to remember nano is times 10 to the negative 9. And we're working in Kelvin, always in Kelvin. Well, here it's meters Kelvin, not millikelvin, right? Because we want our constant to have the same units, meters from our wavelength and Kelvin from our temperature. So something that's really hot, right? We also think about this in terms of stars. If you get a white star or a blue star, it's going to be much hotter than a yellow star or a red star, right? And that's all based on this black body radiation. And what's really happening, this is a little bit deeper than we need to get, but what's really happening is we're having those atomic transitions in all of the atoms in this super hot star. And when it's hotter, right, we're going to have more energy in those atomic transitions. The electrons are going to be able to transition further away, and as they come back down, they're going to release more energy, which actually means a shorter wavelength, right? And if you're cooler, you can't have that large of an energy transition, not as much energy. You're going to have a shorter wavelength. So, a longer wavelength. And in physics, the longer wavelength radiation has, the lower energy, right? And that's why red is our lowest energy and our least bright. Also the lowest energy density, which is joules per meter to the 4. So math for Wien's law isn't that crazy hard, and you're given the formula. So these questions should be a bit of a relief if they do come up on your IB papers or on a unit test, because all we're doing is using the constant that they gave us and making sure that we have the correct units, meters and Kelvin. So sun is approximately black body spectrum, and most of its energy is radiated at this wavelength, 5 times 10 to the negative 7 meters, which would be about 500 nanometers. And if we go back here, that's yellow, which makes sense because the sun kind of appears yellow to us. If we want to find the surface temperature, we're going to use Wien's law. So temperature would equal our constant divided by our wavelength of that majority or highest energy, right? So that peak. So most of the energy is radiated, represented by the peak of our energy density, right? So more energy is being radiated at that peak wavelength for that black body. So each of these lines really is representing a different black body that's going to be absorbing and emitting different wavelengths, right? And they'll each have their specific peak wavelength. So the sun, 5,800 Kelvin from Wien's law and its color, or the visible radiation wavelength that we see it primarily radiating. All right, now we have the Stefan-Boltzmann law, which is the amount of energy per second, power, radiated from a body, which depends on the surface area and the absolute temperature, according to this formula, also given on our formula sheet. This one is the Stefan-Boltzmann, and you have this sigma here, which is our Stefan-Boltzmann constant, which you can find not here, but somewhere else on our formula sheet. I'll just try to navigate that for you as well. Here we go. Stefan-Boltzmann constant, different than Boltzmann constant, Boltzmann was a busy man. We've got 5.67 times 10 to the negative 8 watts per meter squared per Kelvin to the 4. Right, just what we have here. So we need to be able to navigate our formula sheet to find our Stefan-Boltzmann constant. We also have to remember what this lowercase e is. So that's the emissivity of the surface. So it'll be 1 for a black body like the Earth or the Sun. And as it kind of deviates from that perfect black body criteria, as it isn't quite emitting or absorbing all of the radiation that is in contact with it, you're going to get a smaller emissivity. So emissivity is just how much of the incident radiation it will be emitting. So 100% would be a 1. So let's do an example with this formula. This one's kind of a weird. IB likes these types of proportionality questions. We've got to be ready for these on the papers because they always come up. By what factor does the power emitted by a body, right, or kind of assume a black body, increase when its temperature is increased from 100 degrees Celsius to 200 degrees Celsius? So even if it wasn't a black body, we would just change our emissivity. But as we're changing temperature, right, we're going to hold our emissivity constant. Obviously, the Stefan-Boltzmann constant will be constant. It's right in the name. All we're changing is the temperature. So if we look at our formula, everything is staying the same on this object but temperature. So if you're trying to create a fraction, or in this case, the factor, we need to find our final divided by initial. So everything will cancel, all of our emissivity constants, area, except for temperature, and we'll be left with our final temperature in Kelvin. So we need to add 273. So we get 473 to the power of 4 as our final temperature, divided by our initial, which is 100 plus 273 Kelvin. We get 373 to the power of 4 Kelvin. So we get 2.59, a factor of 2.59 increase of the power. So we're changing our body's power by 2.59 times. This is some more conceptual stuff, kind of a bit of review. The sun emits electromagnetic waves, so everything from gamma, X-ray, UV, visible, infrared, microwave, and radio waves in all directions. Right? It's not just a laser beam pointed at the Earth. It's going everywhere. Some of them, right, a pretty small fraction of them will reach the Earth. And now we're getting into this idea of albedo, which is our last formula on topic 8. Albedo is the total scattered power divided by the total incident power. So around 30% of this radiation from the sun, or these electromagnetic waves, will reach the Earth. 30% will be reflected of that reaches the Earth, and that's called Earth's albedo, which is 0.3. 30% is reflected. Albedo will represent how much is being reflected. The moon's albedo is 0.12, representing 12% of what reaches it being reflected. So it's actually going to hold on to more of the sun's radiation than the Earth will. So albedo is the ratio of reflected light to incident light, right? In our formula sheet, it's the power of that reflected, right? It can also be, right, just thought of as the energy. They'll give you the same results. So more into this idea of albedo. The albedo of a body is defined as the ratio of power of radiation reflected or scattered from the body to the total power incident to the body. So let's look at the snow side here, this white block. We have sunlight coming and hitting it, right? That would be the total incident power. We're going to have some of it absorbed, some of it reflected. So the total power of the reflected divided by the total power that came in will give you your albedo. Right? Total scattered, which is reflecting off, divided by the total incident. So we're concerned with those two yellow arrows. The red arrow, which actually, even for ice, should be bigger than that, I would say, is what's being absorbed by the body, in this case, the ice on the earth. Right? And then in the water, we're going to absorb far more. So the albedo of the earth being 30% is a combination of the snow and the water on the earth's surface. Right? Where you'd have a much higher albedo, lower, because we're scattering less than the incident. So albedo is total scattered, this small arrow, divided by total incident. We're going to have a small albedo because we're absorbing, not reflecting. So think of albedo being the reflectivity almost. And you'd have a higher albedo because you're scattering more compared to the incident on ice. So albedo will fluctuate on Earth. The albedo depends on the ground covering. So ice will be a high albedo, higher reflectivity. Ocean low because it's going to absorb more. Clouds, right? Clouds are often white, so they'll be similar to the ice. They'll reflect a bit more. And there's other factors as well, like the terrain on the Earth, rivers, lakes versus mountains, and this is kind of what we need to focus on, ice versus ocean. So if we're reflecting approximately 30% of the rays from the sun, that means that the remaining 70% is going to be absorbed by the Earth's surface. What happens next? It'll obviously heat up the Earth, right? We're going to absorb that radiation. The atoms and molecules within the Earth's surface and the whole Earth will gain that energy, right? Heat up, which we remember from topic 3 means the molecules will gain energy, they'll start vibrating more. And as a result of that, and this idea of black bodies, anything that is at a certain temperature will be emitting a certain form of radiation, even humans, where humans will be emitting infrared. The Earth is similar, right? It's cool enough that it's only emitting these very large wavelength, low energy forms of radiation in the form of infrared. So the absorbed solar energy is re-radiated at longer wavelengths. So the Earth is kind of like this converter from these small wavelengths all the way from gamma, right, to visible. On average, it would be that smaller wavelength visible, like 6,000. It's going to convert that, 500, 600 nanometer wavelengths, convert it to infrared, which is much larger. So in the infrared region, we're emitting back out into space in all directions. So let's use what we know about Wien's law and the Stefan Boltzmann constant to determine the temperature of the Earth if we had no atmosphere. So the solar constant, meaning that's what the sun is constantly giving off, is 1,360 watts per meter squared. All right, we went over that in topic 4 when we talked about intensity. This can only shine on one side of the Earth at a time, right? If we're trying to find the power that the Earth is receiving, we just want watts. We want to get rid of the meter squared, which is a unit of area. So we're looking for the area that the Earth is actually going to be absorbing this solar radiation from. So it can only shine on one side of the Earth at a time. The silhouette of the Earth is a circle, right? The area of a sphere, cross-sectional area, would be the circle. So we're going to use pi r squared, which is area of a circle, where the radius, the r, is the radius of the Earth, 6.4 times 10 to the 6 meters. You can find that on the formula sheet as well. So the power on the Earth from the sun is 1,360 times pi times 6.4 times 10 to the 6, and that radius is being squared. We're getting 1.75 times 10 to the 17 watts. So we want to find the temperature from this power on the Earth. So we're going to need to use Stefan Boltzmann and this idea of albedo. So 1.75 times 10 to the 17 watts. We're only absorbing 70% of that, so we'll need to multiply that by 0.7, giving us 1.23 times 10 to the 17, because we're reflecting 30% of that power incident on Earth. So at equilibrium, Earth acts like a black body where our emissivity is 1. The power absorbed is the power emitted. So we'll use this power is equal to emissivity, Stefan Boltzmann constant, area, temperature to the 4. We're solving for temperature. So using Stefan Boltzmann law, 1.23 times 10 to the 17 equals 1, our emissivity, right? That's where the 1 is coming from. We're assuming Earth is a black body, because it approximately is. Then we've got the Stefan Boltzmann constant, the area of the Earth with the radius as we just used in our previous example and given on our formula sheet. I'll show you where it is on the formula sheet. Radius of the Earth. Why are you not here? So our constant is here. Okay. Must be given elsewhere. Interesting. Well, regardless, you would be given this in the question if it isn't in the formula sheet, which is surprising. It should be. Maybe needs some updating. All right, so that's our area of the Earth, 4 pi r squared. Right, where the radius is 6.4 times 10 to the 6. 4 pi r squared times the temperature to the power of 4. So if we divide this whole side by everything but temperature, and this side as well, take the 4th root to the power of 1 over 4, we get a temperature of 255 Kelvin, which is minus 18 degrees Celsius. So that doesn't seem right. There's obviously more heat coming from somewhere, and that's where greenhouse gases come in. So the absorbed solar energy is re-radiated at infrared, right? The infrared region of the spectrum. And there's gases in the atmosphere, right? We've got carbon dioxide, we've got water vapor, we've got methane. Each of these is going to absorb some of this infrared radiation, and they're going to start vibrating with resonance. So if their structure is the right length to resonate with, or if these molecules are vibrating at a natural frequency. So this is all related to simple harmonic motion, and our waves, if they have a natural frequency of vibration that matches up with the periodic force of our infrared radiation, they're going to vibrate more, right? Resonance increases the amplitude of a wave. They'll vibrate more and become hotter as a result, right? Increased vibration, increased speed, increased temperature. So these are being heated up by the re-emitted infrared radiation from the Earth. And that's what we know as greenhouse gases, which we think is a really bad thing, but in small doses, it's a really good thing. So greenhouse gases include carbon dioxide, methane, water, and N2O. So here's a complicated Sankey chart of the energy being absorbed by the Earth's surface from the sun, being re-radiated. So let's just go over that quick because it is important. The gases in the atmosphere absorb the infrared radiation and re-emit it, where half goes into space but half returns to Earth, approximately. So of that 30% of the incident radiation that is, 70% that is absorbed by Earth will be re-emitting all of that, and then approximately 50% will be returned to Earth because of these greenhouse gases. They'll be absorbing the infrared radiation and re-emitting it. So as one of those carbon dioxide or water or methane molecules is absorbing our infrared, right, it's going to be vibrating faster, it's going to be increasing its temperature, and as it slows down and loses that energy, it's actually going to re-emit that infrared. So this energy has gone through a lot of absorption and re-emissions at this point. But once again, we are re-emitting that radiation in all directions, just like the sun does, but on a much smaller scale. We're talking about a single molecule. So we're talking about very low amounts of energy, where half of it, right, if we think about it being a sphere, approximately half will go out towards space and half will return to the Earth's surface. And it is very complicated. So this could be the energy or the power. They're talking about power here. Power per meter squared. 342 watts per meter squared from the sun, right? Some of it is going to be absorbed by the atmosphere on its way in. So only approximately 169 is being absorbed by the Earth's surface, where 30% is being reflected because of the albedo. Some other parts are being reflected by clouds and different particles. So it looks like 100 out of our 340 incident is immediately being reflected, and then the extra 237 would be absorbed either by the Earth's surface or the molecules, greenhouse gases in the atmosphere. And some of it's going to be heat, just that we feel as humans on the surface, sensible heat. 76 will be latent heat, which is going back to topic 3. That's the heat that's essentially invisible and bound up in our evaporated water, and as soon as that water condenses, we're going to release that latent heat. And then we're also losing heat or the majority of what was absorbed is going to be emitted by surface radiation. I don't know where these extra watts came from. That's a question for a different time. Part of it is coming from the energy in our atmosphere, the greenhouse gases. and black body radiation from these atmospheric greenhouse gases. So we've got 321 from that, an extra 169. So a lot of it is being released as this infrared surface radiation, which is joining back in this cycle of greenhouse gases and infrared radiation being absorbed and re-emitted by the surface and by the greenhouse gases. So kind of mark this up as you will. Take some notes and you don't have to memorize numbers by any means, right? But this idea of some being reflected, some being absorbed, re-emitted as infrared, right? And these cycles of this infrared being partially outgoing, right? Emitted to space, partially coming back to Earth to continue the cycle. That's all going to be important and testable. And yes, it is complex. So there's a balance between the energy absorbed by the Earth and its atmosphere and the energy emitted. So if we kind of disrupt that balance, bad things will happen. So normally the Earth has a fairly constant average temperature. There have been big changes over thousands of years, which we know as ice ages. So without this normal greenhouse effect, the Earth would be too cold to live on, right? We looked at that. Without an atmosphere, the Earth would be minus 18 degrees Celsius on average, and we would have all ice, no water, no life. Most scientists believe that we are producing more of the gases, these greenhouse gases, thus upsetting the balance and producing a higher equilibrium Earth temperature. That's the enhanced greenhouse effect. So the greenhouse effect on its own is a good thing. Enhanced greenhouse effect is a very bad thing, as I'm sure if you've watched the news or been in school over the last 20 years, you are aware of. So with this enhanced greenhouse effect, right, we're kind of starting this domino effect, beginning with the melting of polar ice caps. So this has to do with the albedo of the Earth. Remember that ice is what reflects a lot of those incident solar rays. So the ice is important in giving the Earth that albedo of 0.3. 30% is being reflected on average. So as we're melting more, we're going to have a smaller and smaller albedo, which means that less and less of that solar energy is being reflected and more of it is being absorbed by the Earth to then be emitted as infrared, right, and increase the temperatures of the surface of the Earth. So this is kind of a vicious cycle. As you can see, if we're melting more, we're absorbing more energy from the sun, and we're going to get hotter, and hotter means more melting, and pretty soon we'll have no ice caps. And an important thing to keep in mind and remember is that as these ice caps melt, the water has to go somewhere. It's going to flow into the oceans and raise sea levels. So not good. We'll have flooding of low-lying areas as a result of non-sea ice melting and the expansion of water. So there are normal icebergs and stuff that will melt every year, but it's these large polar ice caps and these glaciers that don't really belong in the oceans. And as we add them to the ocean, right, our water levels are rising, and you're even seeing complete islands disappearing. All right, let's look at the effects of this melting water. This is our last little bit of math in the course, so we can do it. The coefficient of volume expansion is defined as the fractional change in volume per unit temperature change. So this is dependent on whatever we're looking at. It'll be different for anything we're really working with. So we're mostly going to be dealing with this in terms of water. So given a volume, right, our starting volume V naught at a temperature, I don't know why they're not using T, why they're using theta. I'll just go with it. So given a volume V naught at a starting temperature of theta naught, the volume after the temperature increases by this change in temperature, delta theta, will increase by this change in volume, given by this constant, which is the coefficient of volume expansion, times our starting volume, times our change in temperature. So the coefficient of volume expansion is the fractional change in volume per unit temperature change. So that would be change in volume, so meters cubed, or change in meters cubed divided by our change in temperature. So our example for this, the area of the Earth's ocean is about 3.6 times 10 to the 8 kilometers squared, and the average depth is 3.7 kilometers. We're using a coefficient of volume expansion of 2 times 10 to the negative 4 per degree Kelvin. We want to estimate the rise in the sea level for a temperature increase of 2 Kelvin. So we're going to be using this formula to find first the change in volume and then the change in height, rise in sea level. So the volume of the water is our approximate area times our depth. We want to convert our area into, well, we'll do it all in kilometers first. So 3.6 times 10 to the 8 kilometers times 3.7 kilometers gives us 1.33 times 10 to the 9 kilometers cubed, which is our volume. And if you want to go from kilometers to meters, we need to multiply by 1,000, and we need to cube that. So we're actually multiplying it by a factor of 9, right? It's increasing by an order of magnitude of 9. So 1.33 times 10 to the 9 plus 9 is 18. That's where we're getting this big number in meters cubed. And we want to use this number because our coefficient is in standard units. So our change in volume is our coefficient of volume expansion times the starting volume times the change in temperature. So our coefficient of volume of expansion is 2.4 times 10 to the negative 4, right? And that's going to be meters cubed per Kelvin, times 1.33 times 10 to the 18, that's our starting volume, times 2, which is our Kelvin, our change in temperature. So this gives us a change in volume, or an increase in volume, of 5.3 times 10 to the 14 meter cubed. We want to find the raise in sea level, or the change in height. Height is going to be volume divided by the surface area. 5.33 times 10 to the 4 divided by 3.6 times 10 to the 14. Right, and here we're going from kilometers to meters and squaring it. So that would be 1,000 squared, which is 1 times 10 to the 6 more, increase our exponent by 6. And we end up with an increase of 1.5 meters around the world. So, comment on your answer. Stuff's going to be flooding, right? If sea levels are rising by 1.5 meters. This is over 5 feet. That's quite a bit. Some of it will be evaporating, right? A lot of it will be increasing flooding. And this is only for 2 degrees, right? 2 degrees Kelvin, which is equivalent to 2 degrees Celsius. So this is why keeping climate change and global warming down now is so important, because we don't want to be underwater. We're pretty safe in Edmonton, but other people aren't. Other things than flooding, we could have extreme weather, right? Lots of heat waves, droughts, hurricanes, torrential rain, just because we're changing this natural balance. Long-term climate change, if we melt all of our ice caps and then all of our water evaporates because it's so hot, this could be us. We could be the new Mars. And social problems, right? people just will go crazy. Maybe they'll start burning cars because cars create greenhouse gases. The worst thing is actually agriculture. If you look at a breakdown of contributors to greenhouse gases, agriculture, and especially methane, is number one. It's probably at least 5 times as big of a contributor as all of the vehicles on the earth combined. So cars are bad, cows are worse. Evidence: if somebody says that they don't believe in climate change, just tell them to look at the ice cores, the weather records, satellites measuring the change in temperature. Right, ice cores is a nice topic. Maybe I'll throw a video on the Google Classroom. You can kind of trace back to other ice ages. You can also see the amounts of dissolved carbon dioxide from the atmosphere and trace that back to time. And we can see how the change in the carbon dioxide and other greenhouse gases levels in our lifetime is so much more than we've ever seen in really the history of the world before us. Other possible causes of global warming. Yes, these are potentials. We could have a hotter sun, increased solar activity, solar flares. Here's a big one: volcanic activity, increasing CO2 concentrations. If we get a huge eruption, it could really be bad news for humans. Earth orbiting closer to sun, that's another possibility, right? We could be even getting a couple meters closer every year, which in the long run would greatly increase the amount of solar energy absorbed by the Earth and therefore our temperature. All right, we'll wrap it up with our surface heat capacitance review of topic 3. So this is a familiar unit, right? Or formula, I should say. This is our energy required to increase the temperature of 1 meter squared surface, so 1 meter area, by 1 degree Kelvin. So this surface capacitance is measured in joules, which is our Q, right? That's our energy, thermal energy, per meter squared, right? From our canceling out our area, per Kelvin from our change in temperature. So this is the last example, I promise. We have a radiation intensity of 340 watts per meter squared is incident on the surface of a lake of surface heat capacitance, CS, 4.2 times 10 to the 8 joules per meter squared per Kelvin. Calculate the time to increase the temperature by 2 degrees Celsius. So every meter squared of the lake receives 340 joules per second. That's what this means. The energy needed to raise 1 meter squared, so this unit area that we're looking at, by 2 degrees, right? So energy is Q, which is equal to area, surface capacitance, change of temperature. So unit area, we're using 1 for our 1 meter squared of lake, times 4.2 times 10 to the 8, which is our CS, surface capacitance, times 2 degrees Celsius. We need 8.4 times 10 to the 8 joules in that 1 meter squared to raise it by 2 degrees. We want to find how long it takes with this power per area. So time is going to be energy divided by power. So energy, 8.4 times 10 to the 8 divided by power, 340. It would take 29 days. But the sun only shines approximately 12 hours a day, so it would take at least twice that long. We did it! Congrats! Hopefully you enjoyed this unit as much as I did, this course as much as I did. Sad to see it go. I hope you guys enjoy studying, writing your finals. Good luck. Let me know if you have any questions at all, and I will be in touch. Bye.